So to the next question, we are moving on to the question number 4. Two bromo derivatives, that is C6H5CH3Br and C6H5CH6H5Br. Which one will go more is reactive for SN1 substitution? I have told SN1 depends upon the stability of carbocation. So first compound is C6H5CHCH3Br. So I have written C6H5CHCH3Br, if you see that. And here when I release the Br, so carbocation will come over here. Here you can see here it can undergo resonance with the one phenyl group. But in the second case, the compound was C6H5CH C6H5Br. That means this is C6H5CH6H5Br. So if you throw the Br out, so here the carbocation and it will undergo resonance with the two phenyl groups. This one, and but here it is undergo only resonance with one phenyl group. So more is the resonance, more is the stability. So as this carbocation can undergo resonance with both the rings, so that is why it is more stable, and so it will undergo faster SN1, because this carbocation is highly stable because it can undergo resonance with the both of the phenyl group. But here when it's released Br minus, so here positive charge is coming which can undergo only one-sided resonance with the one phenyl group. So that is, it is less stable, it is more stable. That is why C6H5CH C6H5Br will undergo faster SN1 because it is carbocation is more resonance stabilized. Moving on to the next question. Now, next question is SN1 reactions are accompanied by racemization is an optical active halides. That means SN1 reaction, why it undergo racemization? Because there is two things. In SN1, the carbocation is planar carbocation. And therefore, attack planar carbocation means what? It is look like that. If you see it, it is look like this type. The carbocation will be like this. So, if the carbocation will be like this, then attack can be come from the both side. Attack can be from this side also, and attack can be come from this side also. As because attack can be come from the both of the side, that is why it is undergo racemization. Because it is undergo SN1 goes through carbocation formation, and it's a planar carbocation, means angle should be 120. So that is why nucleophile can come from the both of the sides. As the nucleophile can come from the both of the side, that is why it can undergo racemization. So this is why it is written over here. In SN1 carbocations are the intermediate. Since carbocations are planar species, therefore attack of the nucleophile can occur from both of the sides in almost equal ratio. So as both in the equal percentage it is happening, that is why it is undergo racemization. That is why SN1 is undergo racemization for that. So SN1, why SN1 undergo racemization? Two reasons are there basically. One, as because carbocation is the intermediate and carbocation is the planar species, so nucleophile can attack from the both side almost in equal assay. That is why it is undergo racemization. Now, racemization, next question, racemization, racemic mixture is optically inactive, give reason. Now, any racemic mixture is optically inactive. Why? Because it is exactly cancelled by equal and opposite rotation caused by the molecule of another enantiomer. That means one enantiomer, what rotation he is showing, that is exactly cancelled, and opposite can exactly cancelled by opposite, equal and opposite rotation caused by the molecule of another enantiomer. That means what one enantiomer is showing what rotation, another enantiomer is showing exactly opposite and equal and opposite. That is why it is become optically inactive. Racemic mixture is optically inactive because what rotation shown by the one enantiomer is cancelled by equal and opposite rotation caused by the another enantiomer. That is why it is inactive. And as I told you here, I have told that SN1 is undergo racemization. Why? Because SN1 carbocation is intermediate and the planar carbocation, planar mean 120 angle, so nucleophile can come from the both of the side. That is why it's undergo racemization. And here racemic mixture is optically inactive, give reason, and that is the reason for that is as because the rotation caused by the one enantiomer is exactly cancelled by equal and opposite rotation caused by the another enantiomer. Next is dipole moment of chlorobenzene is lower than that of cyclohexyl chloride. It's nothing as because in the chlorobenzene, the carbon is attached to the double bond, so it is sp2 hybridized. Here in cyclohexyl chloride, it is sp3 hybridized. So more is the S character, more is the electronegativity. So here this sp2 carbon is more electronegative as compared to sp3. So as because sp2 carbon of the CCl bond, that means this CCl bond sp2 carbon is less tendency, as because he is electronegative, so he has no less tendency to release electrons. If it has less tendency to release the electron, so that is why as compared to sp3, so that is why the CCl bond will have lower dipole moment as compared to cyclohexyl chloride. I am telling it again. So as because in the chlorobenzene the carbon is sp2, here the carbon is sp3 hybridized in both of the cases. As in sp2, S character more, electronegativity more, so sp2 orbitals are more electronegative than sp3. So sp2 hybrid carbon has less tendency to release because he is electronegative one, so he has no tendency to release electrons. So if he has no tendency to release electron, so polarity is difficult to create polarity. So that is why dipole, if the polarity will be not perfect, then dipole moment also be less. So that is why, as because the carbon, the sp2 hybrid carbon of the CCl in the chlorobenzene has less tendency to release the electron to the Cl atom than sp3. sp3 is less electronegative, so he has no issue like that. Just because there the carbon is sp2, sp2 means more electronegative, so that is why this carbon has less tendency to release electrons, so that is why it has a less dipole moment as compared to this one. Next question, if you moving to the next question, same type of question is there, that why CCl bond length is chlorobenzene is shorter than CCl bond in CSTCl. So in the CCl bond in the chlorobenzene is shorter. Why? Because this chlorobenzene can undergo resonance with the benzene ring. So when this chlorobenzene will undergo resonance with the benzene ring, so this CCl bond become partial, get the so due to the resonance with the lone pair and the benzene, this CCl bond will be partial double bond character, and due to that double bond will form due to the resonance, it will get the partial double bond character, and due to that double bond character, bond length will be the shorter. So bond length will be shorter. So here there is no resonance possible, it will be single bond character, so that is bond length will be higher. So these two questions is very important for the exam of ISC, or this is one is why the dipole moment, why the dipole moment of the chlorobenzene is lower. As I told, it is sp2, it is sp3, it is carbon is sp2, that is a more electronegative, so it has less tendency to release electron to the Cl atom, that is why it is less polar. So that is why it is less polar means less dipole moment, but here it is not like that. Similarly, this question is asked in the just next question, then why in chlorobenzene, why in CCl bond length in chlorobenzene is shorter? Because of the resonance, the CCl bond getting partial double bond character, and that is why it's become shorter. Here there no resonance, so it will undergo, it's the same single bond character. Next is the presence of nitro group in orthopara position increases the reactivity of the halovalence towards the nucleophilic substitution reaction. Actually, any withdrawing group, NO2 is a withdraw electrons. Benzene itself is electron rich compound, but if it has NO2 group, then NO2 will withdraw electrons. So if NO2 will withdraw electrons, so electron density will be getting less, so nucleophile can easily attack on that. So here, as because NO2 groups are there, NO2 group has a electron withdrawing effect, and due to the electron withdrawing effect, the electron density of the benzene ring will be less, so nucleophile can easily attack on that. So that is why the presence of NO2 group in orthopara increases the reactivity towards the nucleophilic substitution reaction. Why? Because NO2 group is electron withdrawing group, so it withdraw electrons from the benzene. As a result of that, electron density of the benzene will be reduced, so nucleophile can easily approach and attack. That is why the presence of NO2 group increases the reactivity. Next is arrange the following in order of the nucleophilic substitution. You can see more the withdrawing groups, more is the reactivity. So here you can see 2, 4, 6 trinitrochlorobenzene will be the highest, then 2, 4 dinitrochlorobenzene, then 4 nitrochlorobenzene, and last one where the nitro group is not there, only chlorobenzene. So more is the electron withdrawing group, more is the reactivity. Next two questions are very very normal questions for the boards. Chloroform is stored in a closed dark bottles, colored bottles, completely filled so that air is kept out, because it will form, you know very well, chloroform react with oxygen in presence of H, which form phosgene or carbonyl chloride. It is called, COCl. It is the phosgene, poisonous gas. And to avoid this problem, you know very well that we will add a little bit of ethanol inside. So if by chance this phosgene has formed, it will react with the ethanol and form a non-toxic diethyl carbonate. Okay, so chloroform is always kept in a airtight bottle filled up to brim, because if chloroform come in contact with the air, it will form phosgene. Phosgene is a poisonous gas, and it's called carbonyl chloride. Phosgene is called carbonyl chloride. So to avoid this problem, we are adding little bit of ethanol inside. So by any chance, if phosgene form, ethanol will react with it and forming a non-toxic and diethyl carbonate. Okay, next is out of ethyl bromide and ethyl chloride, which are the higher boiling point. As because both the ethyl group are common, here it is a bromide, here it is a chloride. Bromide is a larger size, so it has larger van der Waals force of attraction, so its boiling point will be higher. Ethyl bromide will be higher boiling point than ethyl chloride. So as because bromide is a larger size, so it has a more van der Waals force of attraction as compared to chloride, so its boiling point will be higher. Next question is, in butyl bromide is a higher boiling point than tertiary butyl bromide. You can see this is a tertiary. 4 carbon is there, 1 2 3 4, so it is tertiary butyl bromide. This is, and this is it is normal butyl bromide. So here it is branching occur, and due to the branching, surface area will be less, so boiling point also be less. And here no branching, so more surface area, more boiling point. So this is tertiary butyl bromide, as because 3 methyl groups are there. You can see here as branching occurs. So branching occurs means surface area will be less, boiling point will be less. Here the surface area, no branching, so more surface area, more boiling points. We are moving to the next question. Those are all competency based questions, those which are shown by the council. So these are all conceptual questions. Next question, haloalkanes dissolve easily in the organic solvent, then why? Very important question. Haloalkanes dissolve easily in the organic solvents, and why? Actually, see, when you are taking haloalkane putting to the solvent, so there will be new interaction between the haloalkanes and the solvent. Okay, so this new interaction should be in the same strain with the interaction which are already present in haloalkane and solvent. If they are all three will be in the same strain, then only it will dissolve, otherwise not. So what I told, if you put the haloalkanes into the solvent, there will be new interaction formed with the haloalkane and the solvent, and that new interaction should be in the same strength with the interactions which are already present in haloalkane and the solvent. If they are in the same strength, then only it can be dissolved, otherwise not. Okay, so haloalkane dissolve easily into the organic solvent of low polarity such as benzene, ethyl ether, chloroform, because the new force of attraction set up between the haloalkane and the solid molecules should be the same strength as the force of attraction being broken, and the existing haloalkane solvent. What I told, that is in the written, it is given. The new force of attraction between the haloalkane and the solvent should be in the same strength with the interactions happening between the haloalkane and the solvent. Next is again allyl chloride, and hydrolyzed mode is then in propyl halide. Allyl halide is this CH2 double bond CH CH2Cl, and propyl chloride is this one CH3. I have told hydrolysis is gone through SN1 mechanism, so I thrown the Cl out, so carbocation form which is resonance stabilized, and here it is not, as because here it is resonance stabilized, so this compound will be more stable and more easily be hydrolyzed. Okay, so as I told you already before in the video, that hydrolysis goes through the SN1 mechanism. So SN1, for the SN1 mechanism, so first we are throwing the Cl group out, forming a carbocation which is resonance stabilized, and as because it's a resonance stabilized, that is why it has a more stable, so allyl chloride will easily hydrolyzed as compared to N-propyl chloride. We are moving to the next question. Next question is a little bit of subjective type. It's a big question, that a compound A with a molecular formula of C4H9Br is treated with the aqueous KOH solution, and the rate of the reaction depends upon the concentration of the compound A only. So A is a compound and the rate depends upon only compound A. So that is only possible in case of SN1, because in the SN1 only the compound rate depends upon the first compound. The rate of the reaction depend upon the first compound which is taken initially. So here we are getting hints from that compound A with the molecular formula C4H9Br is treated with the aqueous KOH solution. The rate of the reaction depends upon the concentration of A, compound A. That means depends on the only the compound. Okay, that means it is, we can say directly it is SN1. When the another optically active another isomer of B of those compound was treated with aqueous KOH, the rate of the reaction is found to depend on the concentration of concentration of compound and the KOH both. That means second case, which is optically active, where the rate depends upon the compound itself and the KOH. So there is guarantee as because the two concentration, so it will be SN2. So first one is SN1, second one is SN2, and second one is optically active, they have told. So what is the structure? I have told SN1 is SN1 first one. So base will be 3 degree. So matching with the molecular formula C4H9Br, I am writing the compound. This is C4H9Br. Second one is optically active compound. So I have given a chiral center. You can see its chiral center. Here ethyl group, here hydrogen, here methyl, here 4 different groups are, this is chiral, and matching with the formula C4H9Br, so we are giving this compound as a B because it's a chiral. Chiral means it should have a optical active means it should have a chiral center, so that's carbon should have 4 different groups. Here the carbon having 4 different groups. Okay, then out of those two compounds, which one will be converted to the product by inverted configuration? Inversion happened in the SN2. So this compound will go for SN2. Inverted configuration means inversion happens only in the SN2. So here it will undergo inversion. You understand automatically. So it is written aqueous KOH. So OH is entered in the opposite direction. Where the Br is there, but OH is entered the opposite direction. That means inversion happened over here. Okay, this can be possible, only inversion is happen. Next is convert, some conversion is given, and convert toluene to benzyl chloride. Toluene is this, benzyl chloride is this. So that is why we have given Cl2 by UV. So one hydrogen will be replaced by one chlorine by removing the HCl. Then we are giving aqueous KOH. So Cl will be replaced by OH, this is, and K and Cl will go as a side product. So first CH3 by H nu, CH2Cl aqueous KOH, in place of HCl will come. Bromomethane to propanone, very important. Bromomethane is CH3Br. So propanone in this one you can see, which is common name is acetone also. CH3CO CH3. So first I have given CN, then in the CN I have given CH3MgBr ether. If you know that CN is C triple bond N, methyl group will attack on the carbon, open the bond. So as because it's a CN means C triple bond N will be there. So methyl group will attack on the carbon, then bond will open. So it will be CH3, C, one methyl group is attacked. So this methyl group which is attack on the carbon, initially CH3C was there, CH3C is there. One methyl group attacked to the carbon, so CH3 has come. So N will be double bond because one bond you have opened, then MgBr. So into that if you give hydrolysis, so this N will be converted to ammonia minus, this is minus means it is liberating. So N will be converted to minus NH3, that means liberating. MgBr will be converted to minus MOHBr. And here, so this N will be converted to ammonia. MgBr will be converted to MgOHBr, and here O will come. So it will be CH3CO CH3. First of all, we are giving the alcoholic cation, so Cn will come, then we are adding CH3MgBr. Cn is C triple bond N, so this CH3 group will attack on the carbon, open the bond I have told. So CH3C was initially there, then methyl group is attacked, then it will be double bond NMgBr, N will be converted to ammonia by giving hydrolysis, MgBr will be converted to MgOHBr, and here O will come, so it will CH3CO CH3. Next questions are also very important. This is again conceptual question. Why alkyl halides, though polar, are immiscible in water? Because hydrogen bonding is not happening. That is why they're immiscible in water, nothing else. Grignard reagents should be prepared in anhydrous condition. Actually, Grignard reagents are very reactive. So if you give any moisture, that will absorb the hydrogen, it will form alkane. So that is why Grignard reagents are very reactive. They react with the moisture to form an alkane. So alkane will be formed as because Grignard reagent is reactive. That is why if you give the moisture, it is automatically converted to the alkane. Next, convert to the aniline to phenyl isocyanide phenyl. It's an carboylamine reaction. It's an aniline NH2. Then we are giving chloroform, 3 molecule of KOH. In those one step reactions or 1 to 2 steps, we have to give the full equation. That is the rule of ISC only, that when we are going for corrections of that, so we strictly follow that the equation should be balanced if it is a one step reaction or two step reaction. But if it is a more than 2 3 4, then it is not essential that you are giving the side products. So it is aniline to phenyl as on one line. So aniline to the chloroform inputs of 3 molecular alcoholic acid is from H5NC. Please write the side product, otherwise marks will be not given. 3 KCl plus 3 H2O. Chlorobenzene to phenol. First we are giving 2 molecule of NaOH. If I give 2 molecule of NaOH, NaCl and water will be eliminated out. It will be ONA. Then dilute HCl will be given. So it will take the hydrogen and NaCl will go out. So it will be OH. So aniline to chlorobenzene to phenol. That is the conversion. Here if you give 2 NaOH, so one will be replaced Cl. So OH will come. So as because medium is basic, again water will be eliminated out, it will form ONA. Then if you give dilute HCl, so NaCl will go out and you will get the OH group from there. Next is benzyl alcohol to 2-phenyl ethanoic acid. So if you take this is, next conversion is benzyl alcohol. This benzyl alcohol I have already told. Then 2 is, it is, you can see 2-phenyl ethanoic acid. This is 1 and this is 2. So 2-phenyl, it is ethanoic acid. So first we are giving SOCl to pyridine. Side product will be SO2 and HCl. It will form CH3Cl. Then we are giving alcoholic KCN, K and Cl. KCl will go out, CN will come. Then if you give hydrolysis, then CN will be converted to COOH. That is the product. And here you can see it is 2-phenyl only. It is 1 and it is 2 in the 2 position phenyl group is there. So it will be 2-phenyl ethanoic acid. Next conversion is aniline to fluorobenzene. For the aniline to fluorobenzene, it's a very important, it's called Bal-Cheman reaction. If you search that, if it is there, Bal-Cheman reaction. So we are getting the aniline, we are giving NaNO2 plus 2 HCl, because in the name reaction you cannot do any kind, you cannot leave any side product. Everything has to be balanced. So I am writing NaNO2 plus 2 HCl 0 to 5 degree, NaCl and 2H2 is the side product forming Na2 N2 plus Cl minus. Then you are forming HBF4. H and Cl, HCl will go out, you will form N2 plus BF4 minus. Upon heating, here N2 will go from there, BF3 will go, F will come. So this is Bal-Cheman reaction of the all side products. Next is aniline to chlorobenzene. Same process I have followed. Aniline, and if you are giving NaNO2 plus 2 HCl 0 to 5 degrees centigrade, so NaCl and 2H2 the side product forming N2 plus Cl minus. Then you are giving CuBr by HBr, N2 will be the side product, Br will come. Next is acetic acid, benzoic acid to bromobenzene. First I am giving AgOH, so what will be eliminated out? It will be COOH. Then Hans-Dicker reaction. It is Hans-Dicker. In the Hans-Dicker, the starting material is CH3, this benzene COOH. If you give Br2 by CCl4, Br will come, and from the CO will form CO2, and Ag and Br, AgBr will be eliminated out. Next, some balanced chemical equation, chlorobenzene to aniline. This is a very important question for ISC. That is chlorobenzene aniline is a one state reaction. There is 2 chlorobenzene plus 2 NH3 plus Cu2 or 200 degrees centigrade, 60 atmospheric pressure. It will be 2 aniline molecule with Cu2 Cl2 plus H2O. You have to remember this because it's a balanced chemical equation. Chlorobenzene to toluene. Chlorobenzene to toluene is a chlorobenzene. It's a toluene. So I need a 1 CH3. That is why it's called Wurtz-Fittig reaction. Wurtz-Fittig, it is Cl and CH3Cl is there. So 2 NaCl will go out, benzene and methyl will be joined. So this is plus 2 NaCl. Next is chloral to P dash diphenyl dichloroiphenyl trichloroethane. This is called DDT actually. So what will happen over here? See, I have taken chloral is CCl3CHO. Then we are taking 2-chlorobenzene here. From two chlorobenzene each one hydrogen will take the, this is, if you can see here, one Cl, one hydrogen is there, and this is another hydrogen. So these two hydrogen and oxygen, so together it will go, water molecule will be gone. So this carbon will link with the 2-chlorobenzene. So this carbon is linked with the 2-chlorobenzene with the water. So this is called DDT. So again I am telling, this is chloral CCl3CHO. We are taking 2 molecules of chlorobenzene. From each molecule I have taken one hydrogen from the top and bottom both, and H2O is eliminated out. Then we got CCl3CH, chlorobenzene plus H2O. So this is the conversion from chloral to DDT. Next is another reaction, that is give the balanced chemical equation for chlorobenzene to phenyl cyanide. So phenyl cyanide, you have to give CuCN 200 degree pyridine. So chlorobenzene taken, then you are taking CuCN 200 degree pyridine. So CN will come, side products will be CuCl. Next one question, you can see this is a very important question. This is a competency based conceptual question. So here in this molecule I have given Y. See that which side X was there, Y is added to the same side. No change, nothing changed. So that is why this process is inversion. Retention. This process, retention means there is no change in the configuration. Okay, but here you can see where the X was there, Y entered in the opposite side. So it is inversion happen over here. So in this side retention, this side inversion. If both will be there, then it will be racemization. So this process is racemization. They have told you to identify. Again I am telling, here this compound and this compound, where the X is there, see the Y added to the same side, that means retention happen. Where the X is there, Y added to the opposite direction, inversion. If both A and B are there, so that means it's a racemization. So first step here, it's a retention. Here it is inversion, and here it is racemization. Next question is like that only, this type of question. Telling optically active, very important optically active word, optically active compound having the molecular formula of C7H15Br react with the aqueous KOH to give racemic mixture. Understand that racemic mixture forming means what? SN1. You have to see the formula, same formula, and matching and making the optically active means it should have a chiral center. So you have to match C7H15Br and you have to arrange in such a way that it should have a chiral center. Say in this carbon I have given one methyl group, one side ethyl, one side propyl group, and then Br. So it's a chiral. Okay, as because it is undergo racemization. So in the racemization, that means SN1, in the SN1 first step will be carbocation will be formed. I have to explain, if you remember, that that SN1 is the planar carbocation, and then nucleophile come from the both side. If nucleophile come from the this side, so OH will come in left, because nucleophile is coming this side, so OH is coming this side. If nucleophile will come from that side, OH will come in that side. That means it's a racemization happening, both of the cases. So as because it is optically active, so make it chiral center. Match the formula, then put it in this way, that you should careful that carbon should have a chiral center. Then slow process, first one carbocation will form, then nucleophile can attack from the both of the sides. So this thing happening. Distinguish between the chlorobenzene and hexyl chloride or benzyl chloride. Chlorobenzene, as because benzene is directly linked to the chlorine, so it will undergo resonance. Due to that resonance, I have told, if you remember, that in chlorobenzene partial double bond character will be formed between the carbon and chlorine due to the resonance, so bond cannot be broken. But hexyl chloride means CH3, CH2, 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 Cl. That means what? One single bond can be broken by the reagent. That's why, what is the reagent I have taken? I have taken aqueous KOH, then acid. I have mixed the aqueous KOH into it, then acidified with nitric acid, and then give silver nitrate. As because hexyl chloride, which is single bonded, that chlorine can be broken. Here the partial double bond character will be created, cannot be broken, but here it's a single bond. So due to that, it can be broken to the chlorine minus, and so it will give a white precipitate. But here there will be no observation into that. And same type is, it can be bromobenzene. Same explanation, because bromobenzene or chlorobenzene, in both of the cases, chlorine or bromine directly link with the benzene, and due to the resonance, they are forming partial double bond character. But hexyl chloride becomes single bond character. So first you are giving aqueous KOH, then acidified with nitric acid, then you are giving silver nitrate. Here Cl minus cannot be broken due to the partial double bond. Here can be broken, it will give white precipitate. Next is chloroform and carbon tetrachloride. So that's another. So if you give chloroform and chloroform, if you remember, just we have done the carbylamine. There we are using alanine and chloroform and KOH. So we are alcoholic KOH. So we have added aniline and alcoholic KOH. And so when it will attach with the chloroforms, it will form offensive smell of phenyl isocyanide, which is not possible for the CCl4. That is why this reaction cannot be given by the CCl4, but can be given by chloroform, because you are adding aniline and aqueous KOH solution, alcoholic KOH solution. Next, I have given some name reaction. First is iodoform reactions, very important, I2 by NOH. So we are taking acetone, CH3CO, CH3, 3I2 plus 4NOH. Full balanced equation should be given. A name reaction, full balanced equation should be given. All things should be balanced properly, otherwise marks will be not given. So this is iodoform. Two reactions I have given, any of them you can write. Wurtz fatigue is like that. We have just now did CH benzene Cl plus CH3Cl, so 2 NaCl CH2 will be added. Then Hans-Dicker is there. Hans-Dicker, okay. Next, only fatigue, both will be chlorobenzene or bromobenzene. Like Wurtz fatigue, what is one chlorobenzene or bromobenzene and another one alkyl bromide or alkyl chloride. This is alkyl and aryl, both will be there in Wurtz fatigue. But in fatigue, both of the chlorobenzene or bromobenzene. So from the center, 2 NaBr or NaCl will go out and 2 benzene ring will be linked. Okay, next is Hans-Dicker. Hans-Dicker also silver salt of Ag we have done. So here CO2 and AgBr will be side product, Br will come in the benzene ring. So this is Hans-Dicker reaction. Next, Simonini reaction. In the Simonini reaction, what we did, in the Simonini, we take two molecule of CH3COOH, I2 by CCl4. Like in the Hans-Dicker reaction, we are using Cl2 by CCl4 or Br2 by CCl4, but here we use I2 by CCl4. Then these two molecules will join to form an ester, CH3CO CH3 plus CO2 plus 2 AgI. This is Simonini reaction. Frank-Liston reaction already known. CH3 CH2Br NaR by acetone, I will come instead of Br and plus N2N plus NaBr. Schwartz reaction is this one, 2 CH3 CH2Cl plus Hg2F2. If you give, fluorine will come plus L. Those are the questions which we did. These are related to the first chapter of organic, that is alkyl halide and aryl halide.